we saw the equation, we derived an equation for the U, the periodic part of the Bloch function. It was HKU is equal to epsilon U, where epsilon is the eigenvalue for the crystal state, the eigenvalue corresponding to the energy of the states in the crystal. And we had seen that we can focus on the Brillouin zone, just ignore the other part, because these are just periodic duplicate of images of what we have in the Brillouin zone. And we have seen that we obtain a band structure epsilon n of k inside the Brillouin zone, so a spectrum which is a band structure. So this is what we did last time, and now today what we want to address is the occupation of these bands. So how many bands are occupied in the crystal, how many the electrons are going to fill the state in the crystal, give occupied bands, and then there will be an empty band, and we want to address that today.
I have a question.
Yes?
So, I know that to solve the Schrödinger equation, you need to define the potential for
yes,
the system. Yeah, but it seems we've been able to find the energies without specifying.
No. What I showed last time is just general properties, and I have drawn bands, but this could be different in the sense it was just to show some band structure, but of course to get the exact dispersion of these bands, how they are, if it's a metal, an insulator, this will depend on the crystal potential. So we need a crystal potential, and I just drew bands, and I showed you the three properties, general properties one expects that we derived. The first one is that there is this periodicity, so you can focus on what is inside the Brillouin zone, so solve the problem inside the Brillouin zone, and then it's periodic in reciprocal space. So this was one general property. It doesn't depend how the band structure looks like, it's just general. The other property was that it should be symmetric. Epsilon of minus k is equal to epsilon of k. This was also a general property. And the third one is that when one has non-degenerate bands, just a single band separated from the other, at the Brillouin zone edge one expects it to be flat. And this derives from these two properties, being symmetric, the band structure, and being periodic. So these are the three general properties. Otherwise, how the bands are exactly, this depends on the crystal potential. Okay? All right. So now we are also going to talk about the filling of these bands in general. Now there is a problem from the start, that is, if the crystal, if we consider a crystal, which is an infinite system, periodic, we have an infinite number of electrons, and we cannot really talk about filling. We don't know how to handle that. So what we are going to do is that we will consider a finite piece of crystal, and on this finite piece of crystal we are going to impose the so-called Born-von Karman boundary condition. And with this condition we are going to be able to discuss the fillings of the band, the occupation, count the state, and discuss the occupation, and then we will take the limit when it goes to infinity. And this is the proper way to deal when one has some infinity, like the number of electrons. So this is what we will do today. So I will introduce this Born-von Karman boundary condition, and the purpose is to then discuss the filling of the bands, the general properties of what one expects, how many bands one will expect to be filled given the number of electrons in the unit cell. Okay, so Born von Karman boundary condition. So let's consider a finite piece of crystal on which we will impose this condition, and for simplicity I will consider a one-dimensional crystal. So let's consider this. I have a one-dimensional crystal with a spacing A. So this is my spacing, and then I take n very large, and I will have on my piece of crystal, so this is my piece of crystal, I will have a length L that is n times A, my spacing. So this is the length of my crystal, and then I will impose the Born von Karman boundary conditions, which are periodic conditions on the wave functions. So the Born von Karman boundary conditions are periodic conditions on for the wave function so what one will impose is that the value of the wave function here is equal to the value here. So this means C of x plus n A is equal to C of x. So these are the Born von Karman boundary condition on the electronic states, on the wave function. And of course, we consider n to be very large. Basically, when n is very large, one expects that in the bulk part, in the central part, the properties will not depend on the specific boundary conditions. So we will consider n very large, and in the end, later on, we'll take n goes to infinity. But for the moment, to discuss things, we have to remain finite. Okay, so let's see what we obtain in one dimension with this boundary condition. So I have to solve the eigenvalue problem for the crystal. Hc is equal to epsilon xc. I know that from the Bloch theorem that my solution can always be written as Bloch state. So C of k of x is equal to epsilon I k x u k x, where u is periodic. So I can do this. I can imagine that I will append other pieces of crystal. For instance, my Bloch theorem is valid, and then in addition I will impose this condition. So I can still use that but I will impose some additional constraint, that is, on this piece, I want my wave function to have this periodicity. So it's compatible with the Bloch theorem. It's an extra condition, okay? All right, so this is just from Bloch's theorem for my solution. I know I can always write them in that form. And I also know from Bloch's theorem, from the consequences, that I can focus on K inside the Brillouin zone. So in one dimension is K is smaller than pi over A and larger than minus pi over A, with just this equality here that corresponds to what we discussed for unit cells. Okay, so this is just from Bloch's theorem, and now I'm imposing the Born-von boundary conditions on my state here. And this means that exponential I k x u k x must be equal to exponential I k x plus n a u k of x plus n a. But I know that this function, the u, are periodic with the periodicity of the Bravais lattice, so u of x plus na is equal to u of x. Alright, so this implies that here I must have exponential I, k, and a is equal to 1. Okay? And now I have to this gives me, these conditions gives me only a finite number of k that are allowed, that will fulfill give wave function that fulfill the Born-von boundary conditions. So the k that I'm going to obtain from this has to be 2 pi times an integer. So I have that k must be equal to 2 pi over n a times m, where m is an integer. And what one gets from that is one has a mesh of k points that will be separated by an increment delta k, which is 2 pi over n a. So I have a grid of k points inside the Brillouin zone that have this spacing. So the larger n, the smaller the spacing, the denser the grid. Okay, so now I have to have also my k inside the Brillouin zone, and with this condition, this means I have exactly n, where n is the number of unit cells in the piece of crystal. I have exactly n allowed values of k that are inside the Brillouin zone, and that satisfy these conditions. So I have exactly n allowed values. Let's consider m can be odd or even. Let's say that n odd. In that case, if I want to have my k inside the Brillouin zone, I will have m that has to be smaller or equal to n minus 1, because here I took n odd, so in order to have here an integer, I have to take n minus 1, and here I have minus n minus 1 over 2. So if n is odd, these are the values, the integer that I can use, and I have exactly n of allowed m values. So I have exactly n allowed k values. If I had taken n even, I would have the condition here minus n over 2, smaller or equal, and then here I would have only smaller than n over 2, and again I would have exactly n, capital N, allowed value of n, if I had taken this number to be even. So in all cases I have exactly n solutions. Fine. So let's assume we have some band structure of the type. So I'm showing here K and here the energy, and I'm in a one-dimensional crystal, so I'm focusing on the Brillouin zone here from pi over A to minus pi over A, and I know what is outside because I know I have all my spectrum of the crystal that can be represented inside the Brillouin zone. So I'm assuming my crystal potentials gives me this band. Let's do them this way. So symmetric and zero slope at the Brillouin zone edge, and I assume I have another band here. Let's say like this. And I will have some other bands higher in energy. Now my k values on this axis inside the Brillouin zone are going to be points here. So if I take n odd, I will have m equal to 0, m equal to 1 here. Let's say here I'm showing the corresponding m. So this would be 0, 1, minus 1, and so on. I have a regularly spaced grid of k points. Let's say like this. I should have exactly n points inside my Brillouin zone. So this is m equal to m equal minus 2, and so on. And this gives me the key point. And then, of course, I will have these states that will correspond to these key points, that the psi-k, that are the allowed Bloch states that fulfill the Born-von boundary condition. So the conclusion of this is that I will have exactly n k states per band. By this I mean exactly n k state per band that fulfill the Born-von boundary conditions. Okay? All right. Now let's discuss the filling. So let's start filling the bands, and let's have yes?
Does this mean the band is not continuous, it is just points?
Okay, if you solve the equation h of k u is equal to epsilon k uk, I mean the equation that we saw, you will get a band. And now I'm discussing the filling. So as I mentioned, we have a problem if we consider the infinite crystal, because we have an infinite number of electrons and we cannot, that's not the proper way, it's ill-defined. I mean, we have a problem to fill. So we consider a finite piece of crystal and we impose this boundary condition, which are rather soft boundary condition that are there because then I know that I have a certain number of electrons per unit cell. This is imposed by the chemistry, the atoms I have in my unit cell, and from there I will be able then to fill the bands. So what I'm discussing today is just filling the bands, and I impose these boundary conditions. I mean, some boundary condition exists somewhere in the crystal. You will have somewhere that the wave function will be almost equal or equal. Actually, the exact boundary condition you impose are not so crucial, as I mentioned, because when one will have a very large crystal, one expects the state inside the crystal not to depend on these boundary conditions. But we need to do that, consider a finite piece of crystal in order to discuss the field. And you will see that what one obtains for the filling is robust. That is, has some general properties, and then one can take the limit n goes to infinity, and one has the same condition that one sees for finite. So it's something that is extendable to infinity, but is robust, has always the same property for finite n. You will see that soon. Okay, so here it's just to fill for the filling purpose. So let's have, consider n electron. We consider we have n electrons in the unit cell. And this depends on the chemistry, which kind of atoms you have in the unit cell. So in the slab, in my finite piece of crystal, in the crystal slab, I will have exactly n capital N electron, which is the number of unit cell, times N electron. Okay? So let's take an example. We have hydrogen in the unit cell. So in my one-dimensional cell that crystal that I showed before, the points are hydrogen atoms. So I will have one electron, in this case per unit cell. And therefore, exactly, well, N elect is going to be the number of unit cells in my piece of crystal. Now, for each of the pk state I have here, so exponential ik r x my uk, that corresponds to the eigenstate here. For each of these ck, I can have two electrons because I have also the spin states, so it can be spin up or spin down, alpha or beta. So I can have two electronic states from this pk. So I can have two electronic states with spin up or spin down. So this means I have pk spin up and I have pk spin down. So for each of these states here, pk, I can occupy it with two electrons. I'm also, of course, here considering non-magnetic systems. So I have to fill exactly n over 2 of these states, given the number of electrons I have in my piece of crystal. So I have to fill n over 2 k states. And of course, like in the hydrogen in the atoms, you fill starting from the lowest state until you have used all of your electrons in your system. So I have to fill exactly n over 2 k states here up to my total number of n, where n is the number of electrons in my system. In the case of the hydrogen atom, when I have one electron per unit cell, I will have exactly half of the band filled. Okay? Because the full band would correspond to n k state, and I have to fill n over 2 because each of these states can be filled twice with spin up and down. So in the case of one electron per unit cell, I'm going to fill half of the first band in my crystal. So in my drawing here, I will fill up to I will fill up to here, all the states here. Okay. So in the region I must have here must be exactly half of the length of the Brownian zone. So in this region I will have exactly n over 2 states, and I will fill my bands up to the position where this length is exactly half of the length of the Brownian zone. Okay? In that way, I fill the lowest state up to the number of electrons I have in my crystal. All right. Is it clear? Everybody agrees? And I mean, this property to fill half of the length of the Brownian zone is independent of n. So this will be extendable, and we have a robust criterion to fill the band. Okay? All right. So this was for 1 electron per unit cell, the case of hydrogen, for instance. Now, let's see. Okay, so this was for 1 electron per unit cell. Now, if I have 2 electrons per unit cell, if I have 2 electrons per unit cell, then I will fill exactly 1 band. Okay? Now, if I have 3 electrons per unit cell, I will fill completely this band, and then I will fill half of the next one, but I will, of course, start filling the lowest state, so I will start to fill here up to the correct number of electrons in my system. So I will fill 1.5 band for 3 electrons, and for 4 electrons I will fill the 2 bands. 4 electrons per unit cell. Okay, so this is something robust, general, and extendable to 2 and 3 dimensions. So also in 3 dimensions, if I have 2 electrons per unit cell, I will fill exactly 1 band. So what the Born-von-Karman boundary condition, I can impose them in a 3-dimensional crystal on a piece of crystal. So I will impose for a given length L in one direction, I will have nx times A, ny times B, and nz times C, where these are the lattice parameter. I will impose the corresponding Born-von-Karman boundary condition, and I will have a grid in 3 dimensions, which is analogous to the one I had in 1 dimension, and then I will obtain the same 1 band will correspond exactly to nk state nk states where n is nx times ny times nz. So I obtain the same thing in 3 dimensions, and with 2 electrons per unit cell, I will fill exactly 1 band. Okay? Now this, so I will write that. So also in 3 dimensions. One full band corresponds to 2 electrons. 2 electrons per unit cell. Now, one thing that I had assumed in my drawing, which actually is for an insulator, is that the band I was drawing is well separated in energy from the next one. Now, this depends on the crystal potential, and it's not always so. That is what I was showing you is basically for an insulator. Now, if you take another case, where the band structure would be like this. So this is my Brillouin zone, pi over A minus pi over A. And let's say I have a band structure that is like this, where the bands are overlapping in energy. That is, in this energy region, I have more than one band. So this band is not well separated with a gap from the next one. Then, in this case, of course, if I have 2 electrons per unit cell, I will also fill overall one band, but basically it will correspond to a piece of the first band and a piece of the second band, because I have to fill the lower state first. So in this case, if I have 2 electrons per unit cell, basically, okay, I will have my grid of K points. And I have to fill up to an energy my state, so I'm starting from the lowest state and I'm filling, but I will have to fill also the state of the second band, because they are lower in energy than the upper state here of the first band. So I have to fill up to an energy such that the length here, which I will call L1 K, and the length here which is L2K, I have to have with 2 electrons per unit cell that L1K plus L2K is equal to 2 pi over A. That is the total length of the Brillouin zone, in order to have exactly n states that I will fill when I have 2 electrons per unit cell. Okay? So what counts is the projection in K-space of the filled part of the bands, which must exactly amount to the length of the Brillouin zone. So this is for 2 electrons per unit cell. So overall, I'm filling a band in terms of the number of K state, but I fill part of the first one and part of the second one. And this is a metal and this energy here that corresponds to the highest occupied state is the Fermi level. So in this case, I have drawn the band structure of a metal because I have no gap between the lowest unoccupied state and the highest occupied state. Is it clear? You agree? Okay. So just write here what I said. So if I have a metal, and this is a metal, then the Fermi energy is defined. The Fermi energy, epsilon f, that I will call epsilon f, is the energy of the topmost field state field state or field level, well, maybe too many states. So field level in the ground state. In the ground state of the n-electron system. And at 0 temperature. So it corresponds to this level. This is the energy of the topmost field level in my system, and we define it for metal because it's relevant for metals. Okay, so that is it for the example for the one-dimensional system. Now I wanted to show you also some two-dimensional system, but in this case I need to project. So it becomes a little complicated. So let's project this, and I'm also distributing things for the two-dimensional case. Okay, so this is the case of two-dimensional square lattice. So I have my Brillouin zone to the bottom, which is a square, And then I have some band structure that depends on the crystal potential, but here it is assumed to have this shape, I mean parabolic. And there is also a separation in energy between the lowest band, n equal 1, and the second band, n equal 2. So this is an example of a band structure in 2 dimensions. And if I have 2 electrons per unit cell, then I will fill fully the first band. And this way, if I project the area that is occupied in my K-space, in my horizontal plane, I will have exactly the Brillouin zone. And all state from the Brillouin zone, all K, will have the psi K of n equal 1 of the first band occupied. And I have a spin up and a spin down, so I'm filling overall 2 times the number of cells I have in my piece of crystal. Okay? So with n equal 2, one would fill fully the first band. And if I have now 1 electron per unit cell, then I have to fill up to a Fermi energy epsilon f, such that the area that is projected on the plane, on the horizontal plane in kx, ky, is exactly half of the Brillouin zone. So 1/2 of 2 pi over a square is the area I should have here in order to have the number of electron, 1 electron per unit cell times the number of unit cells in my crystal. So the condition for the Fermi energy with 1 electron per unit cell is that you have to have it at a position such that the projection of your band on the horizontal plane in K-space must be equal exactly to 1/2 the surface of the Brillouin zone. Okay? That way you have exactly n K-space, K state occupied, which is the n over 2 pi, sorry, K state occupied. Okay? Alright, so this is the drawing, and now I will write it. So, in my 2-dimensional case, which is still drawable, with 2 electrons per unit cell, with 2 electrons per cell, I have the band 1 completely filled. And with 1 electron per unit cell, I have to fill my first band, fill until the projected area which was called A in my drawing, in the drawing there, in the KXKY space. So in my KSKY plane is 1/2 of the surface of the Brillouin zone. So this gives me the condition that determines the Fermi energy. So I have to fill up to an energy epsilon F that gives me this area A. Okay? The drawing still there. The energy and my surface A. So that was for the two-dimensional space or two-dimensional lattice, the square lattice. So this is for the two-dimensional case, which was a square lattice in the drawing. So this is for the two-dimensional case. In three dimension, of course, one cannot draw anymore the band structure fully. So what one does normally is that one represents it along some high symmetry direction along the axis of the Brillouin zone. That's the best one can do. So in three dimension, typically one draws the band structure along some high symmetry direction of the Brillouin zone. There, the conditions remain the same. That is the part of the occupied in K space, the volume that corresponds to the occupied state. If one has one electron per unit cell, must be 1/2 of the volume of the Brillouin zone. And again, if you have bands in three dimensions that are well separated in energy, the first from the next one, if you have 2 electrons per unit cell, you occupy fully just one band. Okay? So that's 1, 2, and 3 dimension. Now I wanted to mention also for 3 dimension the Fermi surface. So if in 3 dimension one has a metal, so for instance 1 electron per unit cell will give most generally a metal, but also other situation can lead to a metal in 3 dimension. So in 3 dimension, if you have a metal, or in general in 3 dimension for metal, the Fermi surface is defined as the surface or the pieces of surfaces in K space that have the energy epsilon F. So the Fermi surface are the K such that epsilon of K is equal to the Fermi energy. So in, well, I can show it again in case. In 2 dimension, in the specific case I had here, the Fermi surface is a circle. So in 2 dimension it is a contour, or it can be pieces of contours. If my band structure, the first band was going down again, for instance, I could imagine that I would have a circle, and then I would have also pieces of circle of another band. If my band was doing something like this, I would have a circle here, but I would have also some other pieces of circle. So in general, it is a contour, but it can also be pieces of contours, the Fermi surface for a 2-dimensional case. And in 3 dimension, the Fermi surface are 2-dimensional objects or pieces of objects. Okay? So, and in 1 dimension, these are just points. So, the Fermi surface is the isoenergy surface that fulfills this condition with the energy equal to the Fermi energy. Okay, so that was what I wanted to say about filling. So of course, this condition of having the projected area equal for 1 electron per unit cell exactly to half of the surface of the Brownian zone is a condition which doesn't depend on the specific value of n, capital N, and one can take now n goes to infinity. The condition remains the same, and we have solved the problem of filling the bands in the crystal. Okay? Alright, so now I'm going to move some time to discuss Fermi momentum and Fermi energy in the case of free electron model. So now I'm starting still in the part of the electrons in the crystal on something on the Fermi energy, Fermi momentum in the free electron model. So I will continue. So the subchapter now is on the Fermi energy, and I will define also the Fermi momentum in the case of the free electron model. So the free electron model is a good model, works well for the alkali metals. So for the metals that correspond to the atom in the first column of the periodic table. So the free electron works well for the alkali metals like sodium, potassium, these are the most common. Then there would be also cesium, but these are the most common. So sodium, potassium, and these are elements that crystallize actually in a BCC structure. The crystal is the BCC lattice. So this element has as common feature that they have one valence electron. So sodium, for instance, in terms of electronic shell, has the filled shell of the neon atom, so a rare gas, and then it has n equal 3 s electron, so just one electron in the n equal 3 shell. And sodium is the next one. It has the electronic shell, atomic shell of argon, another rare gas, and it has just one electron, s electron in the n equal 4 shell. So this is the electronic shell of this atom, and they have just one valence electron, one s valence electron. So I mentioned that the free electron model works well for these metals, sodium, potassium, and they are actually a good, the free electron model is a good starting point for other metals, simple metals. So it works well, very well in this case, and it's also a good starting point, let's say, in terms of perturbation theory for other simple metals. Okay, all right. So in the free electron model, the wave function is assumed, the electronic wave function is assumed to be a free electron wave function. So, flat potential, constant potential. Okay, so as I mentioned here, this element and the corresponding have one valence electron, and therefore the corresponding crystal has one electron per unit cell, BCC cell. So one electron per unit cell.
I have
yes.
The whole concept of the valence electrons. Where do we draw the line for the valence electrons?
I mentioned core electrons typically have ionization energy of the order of 50 eV or more. Instead, these typically of the order of the DeV. So, okay, one electron per unit cell. But if you, I mean, from the periodic table, the concept of valence electron is rather straightforward. I mean, here you have an inert element, and then just in the next shell one electron. So clearly, these are will give metals with just one valence electron. Okay, so this have one electron per unit cell, in the sense one valence electron per unit cell, and we will consider just this one. The other electrons are like in the atoms and are deep in energy. So, free electron wave function C of R is just proportional to exponential I k R, which is also a block state with U equal to 1 if you want. So the wave functions are just a free electronic wave function, and the energy is just the kinetic energy h bar square k square divided by 2 times the mass of the electron. So this is the free electron model and the corresponding wave function, and the Fermi momentum is defined by the k that will correspond to the Fermi energy. So I will have a Fermi energy epsilon f, and the Fermi, this condition will give me the Fermi momentum, that is h bar k f is by definition the Fermi momentum. This is the kf is such that h bar kf square over 2m gives me the Fermi energy. So now I have to specify the dimension, because I want to get these quantities explicitly. So within my model, so in one dimension, okay, I have just my Brillouin zone with as edge pi over A. So in the case of one electron per unit cell, I will have Kf, which will be just pi over 2A, that is half of the distance to the edge of the Brillouin zone. This corresponds to a half field band. Half band field. And I can rewrite it just as pi over 2, 1 over A. And this essentially corresponds to the electronic density, that is one electron in my unit cell of length A. So this is essentially the electronic density. And from the argument that we have seen before for filling the bands, if I have 2 electrons per unit cell, I know I have to occupy twice the space in the Brillouin zone. So basically, I can generalize this as Kf is equal to pi over 2 times n, where n is the electronic density. If I had 2 electrons per unit cell, I would just put a 2 here, and this would give me my K Fermi. So the energy epsilon Fermi in the case of a one-dimensional system with 1 electron per unit cell, or n electron per unit cell, is equal to h bar over to m times kf square, which is pi over 2 square times n square. And this gives me explicitly the Fermi energy in one dimension in the free electron model is pi square over 8 times h bar square over m times the electronic density square. So this is the result. In the one-dimensional case, the Fermi energy is proportional to the density, electronic density to the power 2. So if I want to change the Fermi energy, I can change the electronic density. Of course, it's difficult to change the number of electrons per unit cell, but I can change 8. So I could change my Fermi energy by changing my density by changing the length of the unit cell. Okay, so this is for the one-dimensional case. Now I will go to the two-dimensional case. Two-dimensional case. So in this case I will have a circle for the Fermi energy. So this is epsilon kx, and I will have a ky. So I will have a parabolic dispersion in the free electron model, and I will fill up to a kf, and here also. So I will fill, and here I will have in K space I will have a circle corresponding to the Fermi energies. So in the free electron model, my epsilon k is equal to h bar square over 2m k square. And if I have one electron per unit cell, if I have one electron per unit cell, I will fill a disk in K space until the area is equal to half of the original zone. So in this case, so this is Kf, the radius of my circle. Oops, I have to go for this. Okay, I can do it well. So my circle is in kx-ky space, and I fill until the disk has an area pi k Fermi square, this is the area of my disk, is equal to 1/2 of the surface of the Brillouin zone, 2 pi over a square.
Sorry.
Yes?
In one dimension, why did we define Fermi momentum as pi over 2 divided by a? Where does the pi over 2 come from?
It comes from the same condition. So in one dimension, you have your Brillouin zone here,
Yes, but
pi over a, pi over minus pi over a. You have a parabola because we consider the free electron system.
yes, but in this case, can we define the Brillouin zone, because on the edges of the Brillouin zone, the derivative of the dispersion is not zero. This one, chi squared, k squared.
The subtlety is that actually it's degenerate.
Sorry?
The reason why it's not flat is that it is degenerate. But we will see that more in details afterward. The band structure.
I see, yeah.
So it's degenerate
Okay.
and you don't have any more the condition of being flat because I mentioned explicitly that it was for non-degenerate bands. I mean, for a degenerate band, of course, one can still have the condition of periodicity and non-vanishing slope. But for the non-degenerate band, no. So if you have a single band with no degeneracy, then it has to be flat at the Brillouin zone boundary. If it's degenerate, then it's not valid anymore, this property.
So we're just filling the first zone.
So we are
To
just
the half.
filling up
Okay,
to a
okay.
Fermi energy such that this length is equal to half of the length of the Brillouin zone, which is the condition. Okay? Alright, so in 2 dimension we fill the circle in K space up to the condition where the area of this, the corresponding disk is equal to 1/2 the area of the Brillouin zone. This actually is for 1 electron per unit cell. If you had more than 1 electron per unit cell, you could generalize it as so this I can rewrite it as 1 over a square, which is the density in the case of 1 electron per unit cell, and more generally you could just replace this by n, the density, electronic density, because the condition when one has more than 1 electron per unit cell, for instance 2, is that just the area should be doubled. So it's the condition for 1 electron per unit cell is this one. If you had more, it would be this one with here n instead of 1 over a square. Okay, so the condition that I obtained from there is that K Fermi, so this is what I wrote, is equal to 2 pi times n, K Fermi square, sorry, K Fermi square is equal to 2 pi n, and my epsilon Fermi in this case is equal to h bar square over 2m K Fermi square, that is h bar over 2m 2 pi plus n, and if I we write this. I have pi h bar square over m times n. So this is for the two-dimensional case. So in two dimension, the Fermi energy is proportional to the density. Okay, and we can just finish onto the three-dimensional case. So in three dimension, I will not draw, but the condition remains analogous. That is, in K-space, since we have a band structure that is the same in Kx, Ky, Kz, we have the free electron model. So the Fermi surface will be a sphere, and I have to fill in K-space the K-sphere up to a Fermi momentum such that the volume of the sphere, 4 pi over 3 K Fermi square cube, is equal to 1/2 the volume of the Brillouin zone, 2 pi over A cube. And again, so this is equal to 4 pi cube times 1 over A cube, and this is just the density. So if I want to generalize this to 2 electrons per unit cell, I will just replace this by n and have a 2 over A cube here. The
No H bar. Just to be sure.
Allora, no, because we are talking about occupied space in K-space. So this gives me K Fermi cube is equal to 3 over pi times, okay, I write it this way, pi cube times n. Yeah, that's good. I think it's okay. Yeah. And therefore the Fermi energy epsilon f is equal, which is equal to h bar square over 2m times k Fermi cube square, sorry, is equal, replacing that, is equal to h bar square over 2m times 3 over pi to the power 2/3 times pi square times n to the power 2/3. So I replace the K Fermi here. I'm having a power 2/3 of this quantity. Okay, so actually in 3 dimensions the Fermi energy is proportional to the density to the power 2/3. We had seen in 2 dimensions it is proportional to the density to the power 1, and in and in 1 dimension to the density to the power 2. And it's always related to the fact that the Fermi energy has always this factor, and then has K Fermi to the power 2. And K Fermi, it has the unit of 1 over a length. So here from the density to have the unit 1 over the length square, you have to have a power 2/3, because the density goes like 1 over a to the power 3, and therefore to have the unit 1 over a to the length unit 1 over a length square, you have to have a power 2/3. In 2 dimensions, you have already 1 over a square for the density, so you have immediately the kf unit square, the 1 over the length square, and in 1 dimension you have 1 over a, so you need a power 2 to recover the correct unit for the energy. So it's you can get it back from the units. Okay, so I will stop here for this time. And on first day we will see something else, which is the density of states. Any question? All okay?